Have you ever pondered over why glass shatters to bits when dropped, while a copper penny can be bent without snapping, or why a rod of aluminium bends more readily than a rod of steel? These are questions that hinge on the properties of materials. Every material around us, from the glass in your windows to the copper wires in your devices, possesses unique properties that define their behavior and uses. And today, we'll delve into the heart of these intriguing characteristics. Let's start with the brittle nature of glass and the ductility of copper. Glass is brittle because its atomic structure lacks slip systems, paths for atoms to move or slide past each other when force is applied. On the other hand, copper is ductile, meaning it can be drawn into thin wires. This is due to its atomic structure that allows atoms to roll over each other without breaking their bonds. Now, consider an aluminium rod and a steel rod. The aluminium rod bends more easily because aluminium atoms slip and slide past each other more readily than steel atoms. This property is known as malleability. What about changing a material's hardness without altering its composition? Take steel with a carbon content of 0.8%, for example. By adjusting the temperature and cooling rate, a process known as heat treatment, we can manipulate the arrangement of the atoms, thereby altering the hardness of the steel. Swinging over to the realm of conductivity, copper wires conduct electricity due to the free-moving electrons in its atomic structure. Conversely, a piece of brick or wood does not conduct electricity, as they lack these free electrons. And have you ever noticed how glass is transparent while a typical metal is opaque? This is because glass allows photons to pass through without absorbing them, while metals absorb photons and re-emit them, giving them their shiny appearance. Heating copper and silicon reveals another fascinating phenomenon. The electrical conductivity of copper decreases upon heating as the increased thermal energy disrupts the movement of free electrons. In contrast, silicon, a semiconductor, sees an increase in conductivity with heating, as more electrons gain the energy to jump into the conduction band. Iron corrodes easily because it reacts with oxygen in the air, forming iron oxide or rust. Aluminium, though, appears not to corrode because it forms a protective layer of aluminium oxide on its surface, shielding it from further reaction. Did you know that a molten material can be held in a liquid state below its melting point? This phenomenon, known as supercooling, occurs because the formation of a solid structure requires a small nucleus to start the process. Without it, the liquid remains even below its freezing point. Ever noticed bubbles forming around the straw and glass walls in a fizzy drink? This is due to nucleation sites, small imperfections or scratches, where gas bubbles can form and grow. The melting point of a substance is the temperature at which it transitions from a solid to a liquid. It is indeed different from the freezing point, which is the temperature at which a liquid becomes a solid. Curiously, good thermal conductors are often good electrical conductors. This is because both properties rely on the movement of free electrons. Yet diamond, while a good thermal conductor, is not a good electrical conductor. This is because, while its rigid lattice structure allows for the rapid transfer of heat, it does not have free electrons for electrical conduction. Lastly, consider a spring and an aluminium rod. On releasing a stretched spring, it returns to its original shape due to a property called elasticity. However, an aluminium rod, once bent, does not regain its original shape as it is malleable and not elastic. Today we've journeyed through the fascinating realm of material properties, understanding why glass is brittle, copper is ductile, and why a piece of wood won't conduct electricity. Each material, with its unique properties, shapes the world around us in its own distinct way. And remember, the next time you bend a copper coin or peer through a glass window, there's a whole world of atomic behavior at play.